Hey guys, so we're going to do applications of rating measure. This is lesson 9, so I know it says 1.3. We're teaching it in a different area this year. So let's first talk about arc length. Length of a circular arc. If an arc length of S subtends an angle with non-negative rating measure in a circle of radius, then S equals R. So I'm going to kind of explain that a little bit. First of all, what they want is that it has to be in rating measure. Okay. Now, all circles are proportional. So lots of times with formulas, it's very difficult over the years to memorize certain formulas. But what I always memorize is that circles are always proportional. So you can make your ratios and set them equal to each other. So in other words, the arc length, which is S, is a portion of the circumference, which is 2 pi r. And now if we talk about the rating measure, that means theta is a proportion of the whole circle, which the whole circle in radians is 2 pi. Now, of course, if we cross multiply or move to both sides and we cancel out, this is where we end up with S equals R theta. Okay, so let's give this a try. The thing we want to make sure that we're doing first is we must convert to radians. So find the arc length along a circle with the radius 10 subtended by an angle of 215 degrees. So let's convert 215 to radians by multiplying it by pi over 180. And of course, this is a crazy number of 43 pi all over 36. Now, if we actually put it in our equation of S equals our radius, which is 10, times our theta, which is 43 pi over 36, we get approximately 37.52. And we're done. All right, assume that the orbit of Mercury around the sun is a perfect circle. Okay, so picture that right now. The sun and Mercury is going around. Mercury is approximately 36 million miles from the sun. Okay, in one Earth day, Mercury completes 0.0114 of its total revolution. How many miles does it travel in one day? So in other words, we got to figure out in our day, how much would Mercury travel? So what we're going to do first is see how long or what the circumference is of Mercury's orbit. Okay, so circumference is 2 pi r, and the radius of that circle, that orbit of Mercury, is 36 million miles. So I'm just going to say mil, because I know it's mil right there, which is approximately 226 million miles. Okay, and we want to figure out how many miles does it travel in our day. Well, comparative to a 0.0114 total revolution, what we need to do is multiply those two out to figure out how much it completes of the full revolution. So when I do this, I get approximately 2.58 million miles. So that's how much it travels in one day. So use your answer for part A to determine the rating measure for Mercury's movement in one day. So what we're going to do right now is we are going to convert this into radians. So let's think of this. Let's go back to our arc length, which is S equals R theta. We're solving for theta. So theta equals our arc length over our radius. Well, we have our arc length, right? It's 2.58 million miles. And we have our radius, which is 36 million miles. So that means our theta is 0.0717. Now, of course, this is in radians. Okay, so remember, that's a section of the circumference. Next, we're going to do area of a sector. So think of our circle, and we're going to do the like pizza slice of that circle. So again, I can think of this as proportions, right? So our area slice is proportion to our area of the whole circle. So pi r squared, set that equal to our theta. So our theta over 2 pi again. And again, you can rearrange that and we end up with A equals 1/2 theta r squared. There we go. All right, so let's put this into play. An automatic lawn sprinkler sprays the distance of 20 feet while rotating 30 degrees. What is the area of the sector of the grass that the sprinkler waters? So remember, the first thing we need to do is always convert it into radians because that's what we're using. So we have 30 degrees, which technically, guys, we don't need to change this into radians because we already know what 30 degrees is, and it's pi over 6. Now let's figure out that area of the sector. So area equals 1/2 our theta times the radius squared. And we end up with 104.72 feet squared. Awesome. Okay, here we're going to do some more applications. So linear and angular velocity. Suppose an object is moving as pictured below along a circular path of the radius from the point P to the point Q in an amount of time. So here's some definitions we're going to go over. Velocity is that rate at which the location of the object is changing respect to time. Okay. Now, angular velocity, the rate at which the angle is changing. So this is the location. Velocity is the location, the rate at which the location is changing. But angular velocity is the rate at which the angle is changing. If a point is in motion on a circle through the angle of theta radians in time t, its angular velocity, which is represented here, is usually expressed in radians per unit of time. So be careful of time too. Linear velocity, at rate at which the distance is changing. Okay, the distance from an object moving on a circular path with radius r with constant angular velocity w. So it has to be constant. The linear velocity of the object is given by v equals r times w. So let's look at this next example. Assuming the surface of Earth is a sphere, because of course we know that everything's not perfect, right? Any point on Earth can be thought of as an object traveling on the circle which completes one revolution in approximately 24 hours. There's our day. The path traced out by the point during this 24-hour period is the latitude of that point. Salt Lake Community College is at 40.7608 degrees north latitude, and it can be shown that the radius of the circle of the revolution at this latitude is approximately 2,999 miles. Find the linear velocity. So, and it says miles per hour. So the biggest thing with this, guys, is watch out for your units. So linear velocity, of course, is velocity equals the radius times the angular velocity. Okay, but what we need to know is we need to know what the angular velocity is. Now, the angular velocity, of course, is our theta, which in this case is 2 pi r, because we're trying to figure out what's the angular velocity in the whole day, correct? So we go a full revolution, which is 2 pi, and of course this is in radian, and it goes a full revolution in 24 hours. 24 hours. And we can reduce that, right? I don't know why I'm putting that there, guys. There we go. Which, if we reduce this, we get pi over 12 hours. So this is our angular velocity. Now, we know that our distance, our radius, is 2,999, and we're going to multiply it by our angular velocity of pi over 12 hours. And of course, this is in miles and this is in hours, so we're all set. And we get approximately 785 miles per hour. All right, just a couple more. Okay, let's talk about speed. Speed and velocity are closely related, but speed does not include direction. Linear speed is the distance an object travels in a given time period and is the absolute value of linear velocity. Angular speed is the object's angular rotation during a given time on the interval. In calculating angular speed, the radian measure of angle theta is interpreted as a non-negative. So guys, just think of velocity and speed. They're related, except speed doesn't do direction, so you're doing the absolute value, okay? So example 5 here. An old vinyl record is played on a turntable rotating at the rate of 45 rotations per minute. Find the angular speed in radians per second. So first of all, it's got to be positive, absolute value. But as you can see here, guys, we are doing radians per second. And what this is given us, okay, is we are given 45 rotations per minute. So all we have to do in this case, because this is a speed, but we need the speed in radians per rotation. So, or per second, sorry. So in what we're going to do is convert and change these units. So let's talk about the rotation first. We think of a turntable, right? One rotation is 2 pi radians, right? That's a full rotation is 2 pi. And there, the rotations canceled, we're in radians. But now we've got one more thing. We've got to change our minutes into seconds. So in 1 minute, there are 60 seconds. All right, and then when we multiply fractions, we multiply them straight across, and we end up getting 3 pi halves radians per second. So this is how fast it's going, angular wise. Example 6, our last one. A bicycle has wheels 28 inches in diameter. Think of this diameter, which means it's 14 in radius. A tachometer determines the wheels are rotating at 180 revolutions per minute. Find the speed of the bicycle traveling down the road. Now, of course, speed is usually down the road, miles per hour. So that's what we are going to change this to. Now, don't forget too that we need the absolute value. So we're going to keep everything in terms of a positive number. So first, let's change everything to radians per minute. Okay, so we can get into our radians. So we have 180 revolutions or rotations per minute. Let's change this into radians. So we have 2 pi radians in 1 revolution, or 1 rotation, sorry. So right now we have 360 pi radian per minute. Now, absolute values. So we got to think that our velocity here is our radius times the absolute value of the angular, right? So we have our radius of 14. And we have our angular right here of 360 pi radian per minute. This gives us 5,040 pi radian per minute, or inches per minute, sorry. Because we don't need the radian value there, but we know we're dealing with 14 inches per minute. Now, the reason why I point that out is because, yes, we're in minutes and inches, but speed for us is miles per hour. So now we have to do that conversion of changing our inches per minute into miles per hour. So let's start with the 5,040 pi. I'm going to write down my units so I can cross them out in 1 minute. So let's talk about inches. Well, I know in 1 foot, there are 12 inches. So that gets rid of my inches. And in 1 mile, if you guys haven't known this yet, it's a good thing to memorize, there is 5,280 feet. All right, so now I'm in miles, but I'm going to change my minute. So there are 60 minutes in 1 hour. There we go. We're in miles per hour. Multiply straight across. And we get 14.99 miles per hour. So when you do applications, guys, make sure that you're really focusing on those units because that can trick you right there. All right, let's do some practice.